Hi everyone, and welcome to the first of two videos going through some past exam questions on the topic of electronegativity and polar molecules. First question we've got here is the most straightforward one. We need to know this before we can do anything else. What do we actually mean by electronegativity? Okay, and there is a pretty specific definition that they'll want you to say. Okay, electronegativity is the ability of an atom to attract a pair of electrons in a covalent bond. So it's this idea that, a covalent bond is a shared pair of electrons, but they won't necessarily be shared equally if we've got two different atoms in that bond. Okay, they'll be attracted to both atoms, but they might be attracted to one of the atoms more than the other. Okay, and that's what we mean by electronegativity. The more electronegative the element is, the more it will attract the electrons towards itself. In the second question here, it's asking us to draw a diagram of this molecule, so dichloromethane, and we want to show the polar bonds. So here, we're going to have to think about what shape this is going to be. It's a 3D diagram. We've got carbon in the middle bonding to 4 different atoms. So this is going to be a tetrahedral shape. Okay, so we're going to have to try and draw that, and we're going to have to use the wedged lines and the dashed lines to show the 3D shape. Okay, so we're going to have our carbon in the middle. We're going to bond it to a chlorine. We're going to have another chlorine coming off here, and then we're going to have our hydrogen that we want to show as coming towards us, and we want to show one of the other hydrogens as going away from us. Okay, so we have this kind of tetrahedral shape, this triangular base pyramid that hopefully you can kind of see here. And then it says use partial charges to indicate the polar bonds. Okay, now of these elements that we've got here, the element that's particularly electronegative is the chlorine. Okay, if you remember on the periodic table, as you go across the periodic table, electronegativity increases, mainly because the elements are getting more and more protons, so they're better at attracting electrons. And as you go down the periodic table, the electronegativity decreases because the outer electrons are further away from the nucleus. They're not attracted as strongly. Okay, so we want elements in the top right-hand corner of the periodic table are the most electronegative. Remember, you've got fluorine is the most electronegative, and then chlorine is pretty much second in line. So chlorine is particularly electronegative, so it's going to get the delta minus charge. So therefore the carbon is going to have to be delta plus. In this carbon-chlorine bond, the electrons would be more attracted to the chlorine. Every time we think about dipoles, we need to take it one bond at a time. In this bond, the electrons will be more attracted to the chlorine. Okay? And that will also be the case in this carbon-chlorine bond. The electrons will be more attracted to that chlorine. In the carbon-hydrogen bond, the electronegativities of carbon and hydrogen are pretty similar. Neither of them are particularly electronegative. So there is no dipole in the carbon-hydrogen bonds. Okay, so we don't need to put any sort of symbol onto the hydrogens. We then have this question, why is this molecule polar? Okay, now there's a standard answer that the exam board will want you to write. Okay, if it's polar, it's because it's got dipoles in the molecule. Okay, and it'll be because the dipoles do not cancel out. Okay. Why don't the dipoles cancel out? Because the molecule is not symmetrical, okay, or the dipoles are not pointing in opposite directions, essentially. But the way that they'll want you to word it is to say the dipoles don't cancel out because the molecule is not symmetrical. It is usually a good idea as well to explain why we have a dipole in the first place. Okay, so we could say the carbon to chlorine bond is a polar bond because chlorine is more electronegative than carbon. It would probably have made sense to write that first, actually, but it doesn't really matter. This is only a 1-mark question here, so we probably don't need to write this part at all. If this was a 2-mark question, we probably would need to write this in. Okay. Let's look at another example. This is also going back to the work we did on shapes of molecules. So if you're not comfortable with that, it might be worth watching those videos. Here we've got a dot and cross diagram, and it wants us to predict the shape of this SbCl3 antimony chloride. So, right, what's going on here? Well, whenever we do shapes of molecules, we look at what electron pairs we've got, okay? And we always look at the atom that's in the middle, okay? So we can say the antimony atom has, what have we got? 3 bonded pairs and 1 lone pair. Why do the electron pairs matter? Because they repel each other, okay? So we want to say electron pairs repel. And then why have we specified 3 bonded pairs and 1 lone pair? Because they're different. Lone pairs repel more strongly, don't they? So the electron pairs repel, and lone pairs repel more strongly than bonded pairs. And then it's just a case of, have we learned the bond angles and the structures that go with the electron pairs? 3 bonded pairs and 1 lone pair means it's going to be a pyramidal shape. And it doesn't ask for the bond angle, but we would be expecting, if it was 4 bonded pairs, it would be tetrahedral and therefore 109.5. But with the lone pair, it's going to reduce the bond angle by 2.5 degrees. So it would be 107 degrees. It doesn't ask for that, so we wouldn't need to put that if this was the exam. It's then asking us why these molecules are polar. Okay, and again, this goes back to the question that we just answered about the dichloromethane. There is a standard answer to this question. If you have a polar molecule, it's because you've got a polar bond in that molecule. So we need to explain why that is. So it's the same situation that we had before. Chlorine is particularly electronegative. Okay, antimony is not. Okay, so we can say the antimony to chlorine bond is polar because chlorine is more electronegative than antimony. Okay, but just because it's got a polar bond in it doesn't mean it's a polar molecule. For it to be a polar molecule, it must be the case that the polar bonds, the dipoles, don't cancel out. Okay, so it must be that the dipoles in the molecule do not cancel out. And if the dipoles don't cancel out, it must be because the molecule is not symmetrical. Okay, this is a bit controversial, I think, these answers, because the example's definition of symmetrical is sometimes a little bit strange, but it is a standard answer. Okay, what we could do is draw out the 3D shape of this molecule to see what shape it is and check whether it's going to be symmetrical or not. But because they've told us it is polar, this must be the answer, because this is the answer that the example is expecting anytime you get a polar molecule. Okay, if it's a polar molecule, it's because the dipoles aren't cancelling out, and they're not cancelling out because it's symmetrical. That is the answer every single time. Right, finally, we've got another molecule here. It's saying fluorine is the most electronegative element, which we mentioned before. Indicate any dipoles on this molecule below. Okay, well, if fluorine is the most electronegative element, it's therefore going to end up with the delta minus, and the oxygen is going to end up as delta plus, because in this covalent bond, the fluorine is better at attracting the electrons towards itself, and so therefore it ends up with a little bit of a minus charge, and the oxygen ends up with a little bit of a positive charge. And it's also going to be the same in this bond. Okay, remember, we take one bond at a time. Right, finally, suggest the shape of the F2O molecule and its bond angle. So what have we got here? We need to look at the atom that's in the middle. Okay, so this oxygen atom, clearly it's got 2 lone pairs, which they've marked on for us, and it must also have 2 bonded pairs, because that's what these bonds are. Okay. And then again, it's just a case of, have we learned the shapes and the bond angles that match up to the bonding pairs? if these are the electron pairs that we've got, then the shape is going to be non-linear and its bond angle is 104.5 degrees. Okay, because we've got 4 pairs of electrons. 4 pairs of electrons would be tetrahedral, 109.5, but because 2 of them are lone pairs, we're going to take off 2.5 degrees, and then we're going to take off 2.5 degrees again. So we take off 5, and we end up with 104.5.